way downwards. The force in the y direction per story. In the y direction per story, we had the surface area of contact on which the wind was blowing was 35 multiplied by 3. 3 is the story height, 35 was the total length in that direction of the building. So in this column, you click on any cell, you see it's a product of the dynamic wind pressure if column E4 multiplied by the area, which is 35 by 3. And then the force in the y direction per frame, we divided the column F, the force in the y direction per story, divided by 5, because the number of full columns in every story was 5, the inside 4 plus the outer 2, the 2 frames on the edges. Now in the x direction, what changed was just the area. The area in the x direction was 15 multiplied by 3, and we multiplied it by column E, which was the dynamic wind pressure. Per frame, we divided the column H by 3. Column H was the force in the x direction per story. We divided by 3 because the number of full frames in that direction were 2 plus the 2 outer frames. So we divided by 3. So those are the forces in the x direction per frame up to story 18.
Great. I think you guys have done a good job on this wind calculation. I'm very pleased. I think this is the direction to go, and you notice that if you have a rough idea how to work with Excel sheets, you can really ease up your calculations as far as not just these analyses are concerned for wind and earthquake, but also many other structural analysis calculations, things like moment distribution and things like that. So I encourage those who might be amongst us who are not very well versed with Excel. Excel is a really, really good software. It's easy to learn. It's very powerful, though very basic also. And so this is good. Anybody with any question to this group on this particular force calculation before we move on? Anybody who wants to raise any question or concern or comment or highlight a correction for this group before we allow them to proceed? Okay, great. So please, Anthony and your group, you can proceed now to show us the
earthquake forces.
Yes.
Yes, for the earthquake forces, again, we had the story number from 1 to 18. The weight per story we calculated in class. That was the weight of the beam, slab, and column in each story. We found them to be 4,719.72 kilonewtons. So we just inputted those manual values and we assumed them to be equal per story, of which is not the case in real life. But they are shown in that column B. The story height, again, with relative to the ground, from 3 up to 54, as shown in column C. Now, column D is the weight per story multiplied by the story height, which is column B multiplied by column C. If you click on any cell in column D, you can see it's a product of column B and column C. Now, before we find the force in the x direction, which is Fx, we first found the total force the total earthquake force in the building, which we calculated in class. So this value just inputted it there in class. You have in the x direction the total force was 2948.8 kilonewton. In the y direction was 2562.2 kilonewton. After that, we calculated from the CP3 code. That code I can't remember it well, which was explaining how we distribute the forces. First, the top story, and then the other stories, they had a formula. So this FT, the one in red, was the force in the top story, that's story 18 in the x direction, and this they were in y direction. There they had a formula which was if you can click on that cell, we inputted that formula is 0.04 multiplied by h4, which h4 you can see it's the total force, this one here, and then multiplied by C21, which was the sum of this column D, divided by the dimension in that direction, which we are considering. Now we are considering the x direction. The total planned dimension was 35, and it's the whole of that is squared. So we have found the total earthquake force in both direction and the forces in the top stories. Now the remaining force was distributed among the stories using a certain formula, which if you click on this column E and F, you will see the formulas. For example, if you click on column E, you see the formula is product of H4, which H4 is the total force. You subtract the force in the top story. You multiply by column D, which is WX multiplied by HX. You divide by the sum of that column D. Per story, you find the force distributed per story, the remaining force after you've allocated the force that will go on the top story. Again, the same thing in the column Y. The formula is just the same in the product of this, the column I, the total force minus the force on the top story, multiply the dimension in that direction, or divided by the total of column D. So that was it.
Okay, again, thank you. I think this it looks like you understood what we were discussing, and I want to allow the class, if somebody wants to raise an issue or a query or something with the work that this group is presenting, please, you're most welcome to do that. Any question, any comment on what this group has presented? Okay, great.
Sorry.
So, Anthony and your group. Yes, please.
Yes, I myself, I have some concern.
Yes, please, please raise those concerns.
Yeah, we have distributed the force on the top story 18, which is 280.77. But again, here when we distribute the forces, we distribute the forces in each story up to story 18 again. So I was just
you're supposed to distribute up to story 17.
Okay. So I think then we meant
and then the check that you do to confirm that your calculation is right.
Yes.
You see your column number E,
Yes.
You can do a sum at the bottom of total forces for all these floors, and that total force has got to match the value on your cell number H4. You see where H4 is 2948.8.
Yes.
So if your distribution is correct, then the total amount of force at the bottom, including the top floor force, which is 280.77, if you sum all that, should give you 2948.8. That's one of the easiest checks to check whether your calculation is correct.
All right. Thank you. I can allow one of my members to present what we have done on the model.
Okay.
A question before you move on.
Yes, please.
In the calculation of the force for the top floor,
Yes.
the formula was 0.004 F into the height of the building over ds squared, and this ds is the plan of the lateral structural system resisting earthquake forces at the ground
Correct.
floor. My
Correct.
question is, how do we get the ds? How do we calculate the plan dimension for the lateral structural system resisting the earthquake force at ground level?
Okay, so for this hypothetical building, you notice that in plan, the length and the width are not the same. Also, in plan, the building footprint on the foundation is equal to the dimension of that footprint in whatever direction you're considering. So for this particular case, and without going into too much detail to try and answer your question, the dimension that you take when you're considering the when you calculate the earthquake force in the y direction, for example, you simply pick the length of the building in that direction, and in the x direction you pick the length of the building in that x direction. If you can just remind yourself from the notes and the sketch that we did of this hypothetical building. I'm thinking that's what these guys have done, but that's how it's supposed to be done.
Okay, let me just do that and then their value is okay.
Okay. Any other question or concern or comment? It doesn't have to be a question or a concern, you could just throw a comment. Okay, great. So if we're good with that, we'll allow this group to proceed and show us how far they have gone with the modeling. Please, if you can take us through that.
Hello, please confirm if you can hear me.
Yes, Nixon, we can hear you.
So I will share my screen.
Okay. Nixon, are you trying to do this from a phone or something?
Yeah.
Yeah, we can see the face of the phone.
Give me a moment.
Okay. We can see the ETABS first.
Good morning.
Good morning. This is Kagonye.
Yep.
Yes, please proceed.
So this so far we have gone so far. We have modeled our building from story story 1, story 18. We did not include updates so yet. So what so far we have done, we have applied the diaphragm and the loads.
Okay, which loads have you applied?
Live load and dead load. You have to apply the earthquake and the wind load on this model.
Yes, I will show. There are two approaches of specifying the lateral loads, both wind and earthquake, on this particular software, and I will take you through both of them. What we will do eventually for each group, you will have two different files. One, we will manually put in the loadings, both earthquake and wind. And the other one, we will instruct the software with some parameters to calculate for us the wind and earthquake. So we'll have two separate files. And then we'll run an analysis on this one, and maybe at the end we will make a comparison to see whether the outputs are comparable. So that way we'll be able to digest better the thoughts that we are having as part of this work. But I'm seeing you guys are making good progress. I am I am pleased with this. In our next session, I think this will be tomorrow, I will now take you through the thoughts that go into the shear walls, and then we will push this discussion to say, so how do we support the columns and the shear walls at the foundation? And once we have done that, then I will allow us to discuss the thought of, so where is the base? Is it at the foundation or at the ground floor level? I'm still having this question that was asked some few weeks ago. We will discuss that, but that's what I want us to do tomorrow. Now that I'm seeing some of you already are having this model, so that when we discuss the shear walls, then you can go and put them in. And I'll tell you how to, the iterations that I want us to do for the sake of this, for the learning of this exercise, like a learning exercise. I will tell you, please try and put the shear wall here and see how the building behaves, and try and put it here and here, see how the building behaves. We will do this after I have taken you through the basic thoughts of what the shear walls are and how they are able to be effective in stiffening a building in the lateral direction. So thank you very much, this group, for the progress that you're making. I think I am pleased that you have taken initiative and you're making progress. And if we continue like this before this semester ends, which should be almost in about 4 weeks' time, or we're going maybe 5 weeks from now, we'll be doing exams. I hope that you will have learned significantly, and that this course will be meaningful. Now, I want to allow the next group to, again, take us through what you have. Just remind me, lady and gentlemen, we had prepared how many groups? 3 or 4? 2 or 3, sorry. How many groups had we made from this class?
6 groups.
Oh, we've done 6 groups.
Yes.
And each group has 6 members.
Yes, initially each group was having 6 members, but some group, their members left to transport.
Ah, okay. So, okay, let's get the next group. Next group. I am thinking, class rep, since the numbers have become small, we could reorganize these groups so that we have groups of 5 or 6 people, so that we don't have too many groups with just 1 or 2 members each. It doesn't make sense. So I'm waiting for the next group to.
There's no group with less than 5 members. There are 5.
Oh, currently.
Yes.
Okay, perfect. So that means people are not attending this class, because I'm seeing only 21 of us. And that's not good. Yes, sir. I'm in class. Okay, so let's get the next group. And I'm already grading you. I'm taking note which group is doing what. So it will not be just a final submission at the end. So if there's some group that hopes to just copy what others have done and submit, I will not be very happy with that group. The idea is to work continuously. That's how you learn, not to copy at the end and submit a report. So I need to see your progress. So if there's a group that wants to make a presentation and show us what they have been working on, let us have that presentation now. Okay. So if there isn't another group that is ready, I think we can let me continue with the teaching. Teach something small. So
Good morning.
Sorry, who is talking?
Oh, it's Brian.
Okay, so Brian, you will make a presentation in the next session that we have.
Okay.
You'll tell us what your group is and you'll make that presentation. And now that I'm seeing some people want to make a joke of this exercise, I will be grading each group as they make a presentation. So you need to start taking this seriously.
Okay.
Class rep, did you give me the list of these groups?
Yes, sir. It is in your email.
Okay, I'll look it up and start grading you immediately. This exercise, okay, so coursework is supposed to take 60%. I will give you a CAT, it will be 15%. This exercise will be 45%. So anybody makes a joke of this one, you know, you're making a joke with your final grades.
Excuse me, sir.
Yes, this is Muiga.
Yes. Could we reorganize those groups, because some of them are not really functional? I think we can reorganize them, because after the others left, then they were left with they were not really complete. I think we should reorganize them and then now have the presentations, because some of them are not really functional.
So now what we will do, you will liaise with your classroom. And if you want to reorganize them, you will reorganize them. But in the meantime, I think this group that has made a presentation, I am happy with their work. I will award them a mark for this presentation now. And any other group that will make a presentation, I will be awarding marks as we go along, so that I don't get reports at the end that that group did not work on. They just copied, because that also happens. Okay, so you can reorganize. I can have a reorganized list in everything, but I will need to see how the work progresses, not a report at the end. So I want to take some few minutes and talk a little bit about maybe just start us off on this these thoughts on the shear walls. Maybe we can conclude in the next session, and then let's start these thoughts and then we will conclude in the next session. Just give me a moment. I connect this scribbling and then we will proceed. Okay, so I'll put today's date here. Today is 25th, 25. June 2023. So I want us to start off this discussion on shear walls. As to start us off, I want us to consider these two cross sections. So you've got a square cross section with a lighter Put a square cross section. So it's hanging. Let's give it a moment here. Yeah. Now, so we have this square cross section. This section has got dimensions here, 200 millimeters by 200 millimeters. So that's 200, and that's 200. The area of this cross section is 40,000 millimeters squared. And the second moment of area of this section, about an axis XX at the center there, BD cubed over 12, which is B is 200, so we got 200. D is also 200. We got 200 cubed over 12. Please, you will be checking these numbers. I have them in some bunch of notes here. So I'll just put this so that we can go a bit quickly. This is the number that I am getting. Please be checking as we go along. If there's any number that is not correct, let us correct it. Now, consider this other section. Consider this other section of slightly different dimensions. Let this dimension be 100 and this dimension be 400. Again, the cross-sectional area will be 40,000 millimeters squared. And the second moment of area, if we consider that about an axis approximately at the center, x, would be B D cubed over 12. B is 1,000. No, sorry, 100. My apologies. B is 100 times D is now 400 cubed over 12. The number I got for this is 5.3 times 10 power 8 millimeters to the power of 4. These two cross sections have got the same cross-sectional area, and if we were building them in terms of material requirement, we would use the same amount of material. If it was concrete that we needed to build a 200 by 200 element cross-section, we would use the same amount of concrete as we will use in building a 100 wide by 400 deep concrete section. if the length was the same. But you notice that the I value for this section is much higher. Much higher. You know, it's almost 4 times. Maybe it's even 4 times. It's much higher than for the other. So 5.3, 1.33. Yeah, it's 3.98 times. So it's almost 4 times just by rearranging the material on the cross section. Now, also to remind you that the quantity or the cross-sectional property I, which is second moment of area, is actually a measure of the bending stiffness of a material. Is a measure of the bending stiffness of a cross-section. Sorry, not a material, but a cross-section. Is a measure of the bending stiffness of the cross-section. I'm looking for something to illustrate that here, just to remind you. I'll find office is a bit Kenyish. Let me use my phone. This is just a recap of what you have already done in your earlier years, strength materials. So I've got this phone is an element. If I tried to bend it that way, because the I value would be much smaller, it's likely to be easier to bend it that way than if I tried to bend it this way, you know, because the value of I, the bending, the second moment of area that way, is much, much bigger than if we were doing the second moment of area that way, okay? So the I value, basically we bother with it, us as the structural engineers, because it tells us in terms of numbers how stiff a cross section is in bending in about a particular axis. Okay. So with that thought, therefore, then we go back to the hypothetical building that we were considering. We go back to the hypothetical building that we were considering. Maybe I can write a note, remind ourselves that this term from strength of materials, the section property Ixx also we refer to it as the second moment of area of the section about the axis XX is a measure of the bending stiffness of that cross section. Is a measure of the bending stiffness of that cross section. So this is by the way. Now I want us to go back to that hypothetical building that we are trying to design and look at it in the light of this thought that we have just shared here. So you've got 1, 2, 3, 4, 5 bays that way and 3 bays that way. Allow me to re-sketch this building so that there's continuity of these nodes. Two, 3, 4. F5. Huh? We had said earlier, let's assume that we have some square columns. So this is what we had initially. Now, if we were to consider, for example, the earthquake force that is applied on this building in that direction. Okay, so we had two directions. I think we call this Y, we call this X. So if we were to consider that this building is being pushed in that direction, this building was being pushed by a lateral force, which you guys have now calculated in that direction in plan. What is your thought? Do you think it would help to, for the same column area? So we're not increasing the cost of material. We had said we are working with columns of 800 by 800. So for the same size of column, for the same cross-sectional area of column, do you think it would help if we made them elongated in that manner? Ladies and gentlemen, from this building, which you guys are working on, and from this thought that we've just had here, and the building is being pushed that way, would it help to elongate the columns a bit? So same cross-sectional area, so it's 800 by 800. So 800 by 800 is 640,000. Okay, so if we made them 400, 640,000, and then so if we made them 1600 by 400, for example. So instead of 800 by 800, if we made these columns 1600 by 400, do you think it would help? I'm listening to your thoughts.
Yes, I think it would help. Hello.
Yes, it would.
I think it will help because the stiffness will increase in that direction, and
Correct.
that the columns will not bend that easily.
Correct. So what Elijah is telling us is basically what these numbers are telling us. That just by rearranging the element to have a bias in stiffness in the direction where we need the stiffness, it can actually help to stiffen the building significantly. Okay. Now, so even before one introduced walls into this building, just by orienting rectangular columns in a particular direction where we need the stiffness, we can actually significantly stiffen the building and significantly consequently reduce the amount of deflection of the building in that direction. Deflection is something that you will extract from your models once you have done the models. We'll get to that point, and you'll extract deflections, and you'll see as part of the outputs that I want us to do in this exercise that you're doing, just by, for example, changing the column from an 800 by 800 to a 400 by 1600 in that direction, how much reduction of the sway, we call it the sway, the deflection, you're able to achieve. And if you think about it in terms of costs, there might not be a significant change in cost because practically the material quantity is the same. Okay. Now I want to push this thought a little bit further. So we have agreed that simply by making the column rectangular, let's write that as a note, because you after a while, as you go into revision, you might need to remember some of these thoughts. Simply by making this column rectangular, maintaining the same cross-sectional area and maintaining the same cross-sectional area, the building can be made stiffer in the Y direction. Okay, so now I want to wind up this session by asking, how about if we made the wall thinner, the column thinner and longer? For example, if this same column now we made it only 200 millimeters thick, For us to achieve the 64,000 square meters, we will need to have this column have a length of 3.2 meters and 200 millimeters. And I write here, if we made this column thinner, for the same cross-section area, say 200 millimeters, for the same cross-sectional to achieve the better way to say is to achieve the same cross-sectional area, the wall, the column, I'm still calling it the column, would need to be 3,200 millimeters long. Thus, it will have become a wall. Thus, it will have become a wall. Considering the IXX values of the column, the square column, and an equivalent area wall. So IXX BD cubed over 12, 800 by 800 cubed. You can be calculating this by 12. So you got 800 by 800 by 800 by 800 by 12. This is 3.4 times 10 to the power 10 millimeter to the power 4. If we made the wall, if we convert it just by rearranging, then we would have 200 by 3,200 cubed over 12. We would have 5.46 10 to the power 11. Sixteen times. This results in an element 16 times stiffer in bending in the direction of interest. This is the basic concept of the retaining wall. No, not retaining wall, but of the shear wall. That we can actually just rearrange whatever column we have and convert it into a wall, and for the same amount of material achieve a lot more stiffness in a particular direction and therefore stiffen the building significantly in that direction. This is the thinking about the shear walls. I will pause, the keyword is pause. I'll pause this discussion at this point for today, and I'll continue with it when we meet again. And now I will highlight a few other interesting things about the shear wall and how it behaves once we create it or once we allow it onto a building. Then beyond that, now we will put the shear walls onto this building and we analyze and we see the effects of these walls. I want to ask if somebody might have a question or a comment. Please, you can raise it before we close this session. Any question, any comment before we close this session? Great. Now, one more thing. I will, in the course of the day, share with you, and there are two groups that are will be doing structures. There's yourselves, and there's a BTech group as well. So I will share the distribution of supervisors for your final year report and for the BTech group as well. Then I am requesting for a joint meeting. This meeting is just to take you through the thoughts of what you could do for your project. Okay? Asking for a joint meeting between this group and the BTech group. And this meeting, we can have it even in the evening, you know, after you've done your business for the day. We can meet maybe from something like 7. I need 45 minutes, maybe 1 hour, to take you through the thoughts of what is available for you to do as a good project, so that you don't fumble around too much. Of course, eventually, what you will do will depend on your agreement between you and your supervisor. But I feel it's important to start you off so that you don't struggle too much trying to fumble around what you want to do. So I am proposing that the two class reps, Caesar, and the class rep for the other group is a gentleman called John Opar. Please liaise and agree when we can meet and do this, preferably online. But if you strongly feel that you want us to meet physically, we can also arrange for a physical meeting. I will avail this one session only and it's away from your respective timetables, just to discuss the projects. I will share the two lists today. Your list, I will share it with your class rep, and I will share the list for the BTech group with their class rep. But for this session, to start it off, I feel it might be prudent to just meet all of us and I share with you my thoughts so that you get started. Yes, Nixon, you want to say something?
Excuse me, I have a question.
Yes, Nixon, please go ahead.
It's about outputs.
Yes, please.
Please explain the concept of regular and irregular structures.
Sorry, you are not very clear, Nixon. Nixon.
Regular structures.
You're breaking. Just come again, please.
Can you hear me?
Yes, I can hear you.
Please explain the concept of regular and irregular structures and how it affects the stability of the building, of the structure during earthquakes.
Okay, so I think that's a pretty difficult question to answer. But I will make an attempt to take you back to where we were discussing. Maybe you could switch off your mic, with your mic, so that we remove the echo. So I could take you back to where we were discussing the period of vibration of the structure as one of the considerations that you need to take into account as you calculate the earthquake forces. Now, having taken you back there, I will take you back much further, maybe to your third year or your fourth year, I don't know, when you studied dynamics of structures. Now, in dynamics of structures, whatever you studied was that you had a dynamic system where you had lumped masses connected with springs. And then sometimes those connections were also coupled with some damping, which contributed to kill off the vibrations. Now, as you change the form of the structure, two things are changing. One, where ideally you can assume lumped masses changes. Two, the stiffnesses connecting those lumped masses also change. And as you are aware from your third year dynamics of structures, I think, if you change any of the parameters of the system, the period of vibration changes. And if the period of vibration changes, coming back to just this simple standard that we were looking at, the Kenyan Earthquake Code, if you change the period of vibration, you change the earthquake force. I have started making an attempt to answer this question by saying it's a very complex question to respond to. But I've thrown to you some thoughts that would help you to start thinking in the direction of what would be the effect of changing the form of the structure. As a very basic general statement, the Kenyan standard and many other standards suggest that generally you want simple, straightforward plan areas, plan shapes, squares, rectangles, circles, things like that. The moment you start having L's and Z's and U's, etc., etc., then it is the way the structure dances under the excitation force of the earthquake that becomes complex. The complexity is not only a headache in analysis, it's also a headache in real life when this building is actually exposed to this structure. Now, for those who might be interested to dig a bit deeper on this problem, there are two professors who many years ago they did a lot of work on the dynamics of structures in the light of earthquake structures. In fact, I think these two professors, if I'm not mistaken, our director, Professor Koteng, I think he had an opportunity to be trained by them. One gentleman is called Muto, and the other one is called Stodola. They did a lot of work, like a foundational work. Of course, a lot of research has been done in this area to refine the thoughts. But that's a good, whatever work they did is a good starting point for somebody like now at your level who might want to have a good understanding of earthquakes to start from. This is one. Two, now that you have a feel of modeling, on a good software like ETABS, you could pull out hypothetical building with a U shape, for example, same floor area, for example, and same height as the rectangular one that we have. So you just rearrange the area so that you have a U shape. So that means the weight of this building will be the same as the rectangular one that we're doing. Run the analysis for earthquake and see how the building dances in the earthquake compared to this building that we are designing. Now, I am mentioning something that I have not taken you to that point yet. Once we load this building with the lateral loads, one of the outputs that are very powerful from this ETAP software is that it's able to show us the dynamic response of the structure. So if the structure will be swaying like this, dancing like this, it's actually possible to extract that output from this standard and to do that video of, not standard, but this software, to do a video of that. So when we get there, maybe just for your interest, you could do a U-shaped building or an L-shaped building or a circular building with a hollow core, and just calculate, put in the loads once we have discussed how to put those in, and run this model and see how it responds dynamically, and run this other model of this other building, hypothetical, and do that. Generally, it is preferred to just make the building form as simple as possible for earthquakes. For wind, you want to make the surface complex so that it confuses the wind vortexes. This is what we said when we were discussing wind. For earthquake, in the plan area, the simpler it is, the better it is in terms of how the building will respond to earthquakes. I will remind you that I've said this is a pretty complex question that maybe I might not be able to give you a yes or no answer, or this, if this happens, then this will happen. But these are the general thoughts that govern what you're asking. I hope that helps to start you off.
Yeah, thank you.
All right. If somebody, we could have one more question if somebody has a question or something. So please, class rep, in the meantime, arrange, if you could please do me a favor and liaise with John Opar, and you agree when we can have this, preferably in the evening when everybody's relaxed and we don't have much things that we are trying to do. It's good. We do one session on the projects, and then we get started immediately. I'll also propose some timelines for you guys, because I'm seeing a lot of the previous groups, a lot of students from the previous group, they were just caught up with time. Somebody is not able to graduate because they've not finished the project. It's not acceptable. Projects are supposed to be a relatively easy assignment to do. Great. So thank you very much. If we don't have any other question, I think we stop here for today. Have a good morning.